Right. What is a weldability? It said here, the ease with which material can be welded to give an acceptable joint. Meaning, is it easy or difficult to be welded? That's the talk about weldability. Is it difficult or easy to be welded, this material? So because weldability here, it's effects of the hardenability, and also from this hardenability, susceptible to cracking can occur, right? So weldability can pose problem for welder, inspector, engineer. So weldability is measured how easy or difficult to obtain crack-free weld, and also achieve adequate mechanical properties in terms of tensile, in terms of hardness, toughness, ductility. So that is mechanical properties. Yeah. All right. So weldability problem can be overcome through understanding. In order to produce sound weld, it is necessary to know and understand the material properties. So that is what is said here. Before we weld the material, first thing to do is to know the material. Yeah. So that's what is said here. So here, weldability, the first thing here, they talk about the effects of the carbon in the material, and also the grain structure produced. Yeah. Grain structure can be changed from maybe heat treatment, right? So what is the effects of carbon? Carbon here, we can see the percentage of carbon can be from 0.01 up to 1.4%. But this is applied for plain carbon. Plain carbon meaning it only has iron mixed with carbon. All right, so that is plain carbon. It's not really has any other element, okay? But maybe small trace of other element, but main thing here, only iron and carbon. So carbon here, when we look at the percentage of carbon, the higher the percentage of carbon, like what we have here, 1.4%. So what happened here, we can see that the hardness will increase and tensile strength will increase. So there is a correlation between two. Good relation between these two. When hardness increase, tensile increase. But it will reduce the ductility. Elongation percentage here, it refers to ductility. Yeah. All right. So that's the effects of the carbon. So steel alloy can be grouped into 5 main groups. We have carbon steel here, alloy steel, quench temper, heat treatable, chromium, molybdenum, all right? And for plain carbon, which is iron and carbon, so the percentage of carbon can be up to 0.3, so they call it low carbon, and medium carbon up to 0.6, and high carbon when percentage of carbon goes up to 1.4%, okay? All right, in alloy steel, it said here, alloy steel contain iron and carbon plus other elements to give steel required mechanical and metallurgical properties. Besides that, we only have ferrum and carbon. So for low alloy steel, when percentage is less than 7%, it contains manganese, chromium, nickel, molybdenum, but all those percentages less than 7%. So high alloy steel, when it's referred to percentages of the element more than 7%. Again, we got manganese, chromium, nickel, molybdenum mixed with carbon and ferrum. All right, so you guys please memorize a bit about what is it manganese for, right? And what is the aluminum for? Maybe they ask you. Okay, so put slightly memorize a bit. So manganese, primary desulfurizer and also secondary deoxidizer, added to steel to reduce carbon, and also it will affect strength. The strength here always refer to UTS here, right? Tensile strength and also hardenability. So aluminum, it will affect mainly in grain refiner. Grain refiner mean you may get smaller grain. When you add more aluminum, you got more fine grain in the steel, right? And I would like you to memorize a bit about this, all this, molybdenum, chromium, and nickel, all right? Please memorize a bit about these things. Possible they ask you. So molybdenum is improved creep resistance and temper embrittlement. Creep resistance here, for example, we have pipe installed in a plant, like a gas processing plant. When there is pressure together with the heat, right, gradually the pipe becomes distort permanently. So that is creep. The pipe distorts permanently when it got pressure and also the heat applied to the material. That means by creep, distortion permanently. Then to avoid creep, then the steel must have molybdenum. Yeah. So chromium, what purpose of chromium? Here is improve hardness and resistance to wear, especially in stainless steel to give corrosion resistance. So that is the purpose of chromium. And also chromium, they add also chromium for high temperature. Normally for high temperature. All right. Nickel improves strength and toughness. All right, highlight this toughness for nickel. Yeah. So it will increase toughness, especially for low temperature. Right? When the material you're going to install this material to low temperature, example subsea, then you need to have more nickel. All right? And also give resistance from acid, especially when they put in austenite stainless steel. Okay? All right. We talk about sulfur and phosphorus here. Sulfur impurities, the things that we don't want, all right, impurities, kotoran lah. Yeah? Harmful because it can cause hot shortness. Hot shortness means when cracking can occur because of high percentage of sulfur. Hot working here can be from welding and also from the heat treatment. Yeah? All right. If the material got very high percentage of sulfur, what happened? The grade, the quality of the material become lower. So it's low quality if we got very high sulfur in material because of the problem with, cracking can occur during welding and also heat treatment. All right. Phosphorus also, the impurities in steel, harmful in steel over 0.5 because it's cold shortness. Cracking occur during cold working. Cold working here can be like rolling, all right, when we form the material, all right, or maybe bending, all right, we bend the material, but because high phosphorus, it will break, all right. So it's again, if we have high phosphorus, then the quality of the steel will be lower. Okay? So they try in steel manufacturing, they are trying to reduce the percentage of sulfur at very low level due to the problem from this element. Yeah, all right. So what is different between carbon content and carbon equivalent? All right. So carbon content, they are talk about the actual amount of carbon in steel. Where carbon equivalent, they are talking about the carbon content relation to other alloy element. Right? So the formula we use like this, carbon equivalent, CEQ, or sometimes they call it CEV. Sometimes they write down as CEV, right? Carbon equivalent. So carbon plus manganese divided by 6, chromium, molybdenum, vanadium divided by 5, and copper and nickel divided by 15. So why manganese divided by 6? Why another element divided by 5? Why another element divided by 15? So reason here is say because manganese has 1/6 the effects of hardenability compared to 1 part of carbon. If we have 1 carbon, then we have manganese. Manganese giving hardness, the properties of hardness only 1/6 compared to 1 carbon, right? It's lower than carbon in terms of hardness, but still it's giving hardness effects. Yeah, right. Do you need to memorize this formula? As far as I know, in your exam, they didn't ask you about the formula. The carbon equivalent formula, they will not ask you, but possible they ask you about what the effects of having carbon, high carbon content. What the effects of having carbon equivalent too high? All those answers will give to increasing hardness. All right, doesn't matter, the question asks about carbon content or carbon equivalent, always related to hardness. The percentage carbon equivalent increase or percentage of carbon content increase, always you have height, hardness. All right, so that's the thing you need to memorize a bit. Yeah, all right, but don't worry about the formula. As far as I know, they didn't ask you about the carbon equivalent formula, so no need to memorize. Okay. Example here we have from, let's say that this percentage of manganese or carbon, you can refer to material certificate, or sometimes we call it MILCER, yeah? Material certificate. So from there, you can start calculate, like carbon, we have 0.12 and manganese is 1.3%. 0.12% for carbon. All right, so now 0.12 carbon plus 1.3 divided by 6 for manganese. Then as a result, we got carbon equivalent 0.336%. Yeah. All right, now we move to grain structure. Because of those two, what they mentioned here. So that is what they mentioned here. Effects of carbon, we already talked about that. And now we're going to talk about grain structure. Yeah, all right. So grain structure and material are influenced by element in material, right? And also temperature during heating and cooling. Heating, soaking, cooling. So that will affect the changing of the grain. Yeah? So critical cooling rate, the rate of cooling from austenite region which determine the final grain structure. Example here. All right, austenite, how we got austenite? So we got austenite grain. Austenite refer to large grain. So that means by austenite. So how to get austenite? Austenite, when you heat material in between 880 degrees C up to 920 degrees C, where they say this temperature, they call it upper critical. Upper critical point, sometimes they call it upper critical temperature, right? So later on, when we talk about heat treatment topic, maybe on the Saturday or Sunday, when we talk about heat treatment, so I would like you to memorize this, yeah? But for today's topic, no need to worry much, yeah? All right. So in upper critical temperature, only 3 processes involved, right? Which is we call annealing, and then normalizing, and then quench. They call it quench hardening. So what's the difference between these 3 processes? Right. We're talking about cooling time. So the time for cooling. When the cooling time takes longer, like what we have in annealing, as a result, we got ferrite and pearlite grain structure. When the cooling time a bit quicker, but not too fast, but a bit quicker than annealing, so that we call it normalizing. As a result, we got grain structure, they call it bainite. But very fast cooling, we got martensite. Later on, I will ask you to memorize a bit about martensite things because of a lot of questions come up with martensite. Yeah? But that will be in topic heat treatment. We will go more details about this. Yeah. Okay. All right. Crack mechanism. We have three types of crack here. We have hydrogen crack, solidification crack, and lamella. All right, but they write down here reheat cracking, but as far as I know, they didn't mention in your exam. So don't worry too much about reheat cracking. And also they didn't discuss in our slide. All right. So what you need to fully memorize a bit, understand more about these three types of crack. Yeah. So that's what we're going to have in your scenario. You're going to have 4 questions from hydrogen crack, 4 questions from solidification crack, and 4 questions from lamella theory. That's what they're going to ask you in your scenario. All right, questions out of 60 questions. All right. All right, now we're going to discuss about hydrogen crack. All right. Before that, hydrogen crack. What is another name for hydrogen crack? They call it delay crack. Write down. This occurs after. They call it delay crack because it occurs after 48 hours welding. Yeah, that's why they call it delay crack. And also they call it hydrogen crack. They call it also HAZ crack. They also chevron crack. They also call it toe crack because it occurs at the toe. Yeah. So it's got many names: delay crack, hydrogen induced cold cracking, HICC, or sometimes they call it hydrogen cold cracking, HCC. Yeah. All right. HAZ crack. Why they call it HAZ crack? Because it's located sometime in HAZ area. Chevron crack because it occurs in the Wellman transverse or 45-degree Wellman. Example like this. Example, we have a weld plate example, and then we got the weld here, the center line weld. Yeah. All right. Example, we have somewhere about maybe like this in the well, which is 45-degree to 45-degree to weld center line. That's why they call it chevron, or maybe it's located in HAZ. So that's why they call it HAZ crack, or maybe at the toe. Yeah. So that's why they call it toe crack. Yeah. It depends on the locations. Is it occur center line in the well? Never. The theory says it's never occur center line. It's always chevron, 45-degree or maybe transverse. That's possible we got transverse crack like this. So that's caused by a chevron. They call it chevron, 45-degree or V shape. So chevron means 45-degree to center line, or it's a V shape. Yeah, so that is chevron. Like you got stopped by police, then you see how many chevron the police got. Sergeant, they got 3 chevron. Oh, okay, this sergeant. Okay, so that's chevron. All right, it's a V shape. All right, a bit memorize a bit, yeah, because of sometimes question asks you chevron crack. What is it chevron crack? Okay, so that thing sometimes a bit detailed you must know a bit, yeah? Because question in scenario is not easy, yeah? Always confusing you, yeah. All right, now we move to this one. So we have factors for hydrogen crack. We got stress, factor of hydrogen, the temperature, and also microstructure. All right. Now I would like you to memorize all this. Memorize the factor for hydrogen crack. This is very important for you. Memorize all this. Yeah. How to memorize? Memorize up to details. You know what I mean? So when you say hydrogen content, it must be more than 50 milliliter. Memorize that one. So hydrogen crack can occur when hydrogen content during welding is more than 50 milliliter. Example, you are using cellulose electrode, MMA, or you using rutile electrode, which is high in hydrogen. All those rutile and cellulose are higher in hydrogen, right? Very high hydrogen. So that is one of the factors. But if you're using basic electrode, which is less than 5, there is no hydrogen crack. And then stress, when it's more than 0.5, and temperature after welding. Example, after welding here, when it's temperature less than 300 degrees C, all right? And also hardness value very high, more than 400 Vickers pyramid number. So basically hardness increase, one of the example how we got hardness higher from the carbon percentage and also from the fast cooling. After welding example, very fast cooling after welding with very high percentage of carbon, right? So that you got hardness very high. And microstructure, what is said here, always molten side. When you got high hardness, the grain structure now changed to molten side. Yeah? Fast cooling example, you got molten side grain. Remember, all these 4 factors together, when you have all 4, all right, 4 factors, 4 brothers together, then you got hydrogen crack. But if you remove 1 factor, only 3 factors, only 3 factors, there is no hydrogen crack. That's what theory say. Yeah. So the easiest one to remove factor is hydrogen. When you remove factor hydrogen, that's the easiest one. There are only 3 factors, there is no hydrogen crack. Yeah. But if you cannot remove factor of hydrogen because of you using this project pipeline, they are using cellulose. So hydrogen factor cannot be removed. Then you need to remove maybe factor of temperature, controlling the temperature to avoid fast cooling. Yeah? Or maybe removing the factor stress. So that only 3 factors, you remove 1, any of these, there is no hydrogen crack. Clear about this? Yeah? And you must memorize this factor, okay? For your exam. Right. So how we got the hydrogen from? Hydrogen can be from shielding gas, or maybe from the moisture of the electrode, or maybe contamination from grease, and also contamination from plate preparation, right? And also you write down here, a bit scarce here, because of you got long arc length. So what is the arc length? Arc length is the distance from the tips of the electrode to the plate. That is arc length. So if the welder using high arc length, so what happened? The coverage, the shielding is not enough to cover. Then the problems there, atmosphere start to enter. Then it will bring hydrogen together. So that's the problems here. So that is source of hydrogen, all right? Now, what's the difference between H2 and here they put H? So H here means that is atomic or atomic. And here H2, they are referring to molecule. Molecule. What's the difference? Atom means single, one. Molecule means group. All right, more than one group, that's molecule. All right. So what happened? During welding, when there is water or vapor, H2O is water. We have water here is combination of 2 hydrogen and one oxygen, H2O, right? So what happened during welding? Because of the heat, it's break the hydrogen and oxygen, so oxygen will escape. But the problem with hydrogen, they are entering, this molecule hydrogen entering the well via the arc. But they are entering one by one. They are not going, you know, when you entering your house with your family, you have grandpa, grandma, uncle, everything. So everybody goes into your house with one go through the door. Not possible. It's only one by one. All right, maybe you go first, and then your grandpa, your grandma. All right, so one by one, they entering the house. It's the same thing here. From H2 molecule group, they are entering the well one by one. Right, single, atomic. Okay, so that is what explanation here. Got it? All right. Hydrogen enters the well via the welding arc. Heat of the arc breaks down molecule hydrogen into atomic. Right? Molecule, we understand this is group. Groups of hydrogen. Atomic meaning is a single hydrogen. Yeah, atomic, single. As well cools down, hydrogen diffuses outward into plate and atmosphere, right? As the well cools, some hydrogen atom can become trapped between grain boundaries as the lattice structure of the steel also contract and change. Below 300 degrees C, hydrogen prefer to be in its molecule form, so individual atoms are attracted toward each other. So what is said here, during welding, the temperature is above 300 degrees C. So what happened? The grain structure now expand. When expand, there is always room, space for hydrogen enter and out. All right, hydrogen will enter and out at temperature above 300 degrees C. They enter one by one, right? In and out, another one coming in, another one come out. But when the temperature after welding drop below 300 degrees C, so what happened? The grain structure now contract to each other. All right, the grain structure contract to each other. At the same time, it will push the hydrogen, single hydrogen, they push from here, push from there, then they are grouping again. Yeah, so that's why here, the hydrogen, the single hydrogen now trapped together with other hydrogen, then they are become molecule again. All right, if the question asks, is it atomic hydrogen or molecule hydrogen create hydrogen crack? The answer goes to molecule hydrogen. Got it? So this is the criminal guy, a group of hydrogen. All right, the one who break the grain structure. When it becomes trapped, then they find a way to break the grain, and then escape. So that will take about 48 hours up to 72 hours. So that's why they call it delay crack. Yeah? Because it takes longer time to break the grain from inside. All right? Break the grain and then escape. Yeah? All right, got it? All right, how to avoid hydrogen crack? We have 4 factors. Then you need to avoid any one of the factors. All right? Clean joint preparation, means removing any contamination. We do preheat, slow down cooling rate. That's the purpose of preheat, to slow down cooling rate. All right? Use low hydrogen, meaning like using a basic electrode in MMA, because basic is less than 5 milliliter. Sorry, my writing, I don't know what happened. Suddenly it's become sharp like that, right? Or maybe using TIG, or maybe using SAW, or maybe using MIG-MEC. Why all this process? Okay, because all of this process below 15 milliliter, yeah, 15, 1, 5, below. So there is no problem with hydrogen crack. Use multi-pass technique. Multi-pass technique like, we have multi-layers, right? Multi-pass, or sometimes they call it multi-layer. We have many layers. Example 1, 2, 3, 4, 5, whatever thickness. The good thing about having multi-layer, we got one layer and then we put another layer. So the top layer reheat treatment bottom layer. Then any residual hydrogen inside the bottom layer will be escaped. If we put another layer, any remaining hydrogen inside this bottom layer will be escaped. So that's a good thing about having multi-layer. Yeah. So to remove the hydrogen, right? All right, here we can see that all those, like MMA, all this TIG, this is lower than 15 milliliter. SAW, flask, or MIG-MAG. And also in MMA, we talk about basic, which is always 5 milliliter, and there is no problem with hydrogen crack. But anything above than 50 milliliter, like we have rutile. Rutile in between 20 to 30 milliliter of per 100 gram, and also with cellulose in between 80 to 90 milliliter. Right, so that is problem with hydrogen here. Okay, you got problem because it's more than 15. All right, we move to next slide. And this is what they said about a scale. We got scale A, scale B, scale C, D, and E. They're talking about hydrogen content. And also in your specification later on, when you are referring to hydrogen content level, in spec also they mention about scale A, B, C, D, E. Do you need to memorize? No need. No need to memorize these scale numbers here. Yeah? Don't waste your time. Eh? Right. But this is the explanation of how to avoid factor of hydrogen, use low hydrogen process, cleaning the material, weather conditions, and use post-heat treatment. Susceptible microstructure, like martensite. We use preheat to delay cooling rate. So that's the purpose of preheat. Temperature here, use post-heat, like hydrogen release technique. Yeah. Stress, how to reduce stress? Reduce wave volume, like single V, you change to single U example. That will reduce the wave volume. Okay, all right, we finished that hydrogen crack, and please just read through all this. Yeah, anything you have problem, then let me know. Okay, and please memorize the factor for hydrogen crack. Got it? Please memorize factor hydrogen crack. I repeat a few times. Okay, that's most important. Okay? All right. Then we're going to talk about certification crack. Again, the factor later on, I would like you to memorize. We're going to talk about certification cracking. Another name, they call it hot cracking. All right, certification cracking or hot cracking. Why? Because this occurs during welding when the material when the joint or the weldment is still hot. Yeah, so that's why they call it hot cracking, and it's always occur in center line of the weld. Yeah, so example here. So what does it mean, solidification? Solidification means from liquid to solid. Solidification means liquid to solid, that solidify. Yeah. All right, remember it's only occur in where? In wear metal. Not like in hydrogen crack. Hydrogen crack occur in wear metal and also in HAZ area. Yeah. All right. Appear a straight line along the center line of the well can occur in a wear crater, mean at the stop well. So wear crater here at stop well. And basically it's easy to see, right? Readily visible. All right, factors, remember we got height, tensile stress, sulfur, and joint geometry. Remember this factor. The next slide, it will elaborate more about all those factors. Yeah? All right, so what is say here? For the crack to develop, solidifying metal must be subject to high tensile stress. This may be result of well metal contraction plus height restraint. All right, restraint here meaning material not free to move. Example, because of thick material. And also because of we clamp during welding or tack weld during welding. All right, so that causes the restraint, we call it. Yeah, height restraint. Material not free to move is fixed. Yeah. All right, we move to the next slide. Remember the sulfur here. All right, sulfur is an impurity in steel which causes low ductile at elevated temperature. Elevated means height, height temperature. Yeah, elevated means height. Create a condition in steel known as hot shortness. The susceptible material to cracking during hot working. Yeah? Free machine steel have high level of sulfur which can cause weldability problem. All right, joint design, joint geometry. Joint design can have significant influence on the level of residual stress. The large gap between components, for example, will increase the strain on solidifying metal, especially if the depth of penetration is small. Well bit with large depth to width ratio are more prone to this type of crack mechanism. All right. I would like you to memorize this, the factor and the geometry here.
So I think we're not having the same slide here.
Sorry?
We're not having the same thing.
You don't have this slide?
Yeah.
Can you take photo of this?
Oh. The same three previous one also.
This one?
The previous one also we don't have.
Oh, okay. So you may take photo of this.
Yes.
Which one? This one?
Yes.
Okay, you may take photo of this. It surprised me. How can you don't have this? Yeah.
Yeah.
But take photo of this, okay? Done?
Okay.
All right. This one? Done?
Done.
Okay, how about this one? Don't have? All right, take photo now. Let me complete the slide. Okay, take photo of this. I will explain now.
Okay.
Okay?
Okay.
All right. Now I will explain about this. This one, depth to width ratio, memorize. Eh? What does it mean by depth to width ratio? All right, it said here for single pass well, it's generally better to have depth to width ratio less than, all right, 1.4 to 1. All right, example here, example, if we have a single V, let's say that single V here, single V, and on this side we have single U example. all right? So let's say that the width, we measure from here to here, the width equal to 20. And let's say that the depth for both these weldment here, we have thickness here, 20 mm, example. And for single U, the width, let's say that we got 10 mm, and the depth will be the same, 20 mm, all right? Okay. Now, depth to width ratio, meaning here, depth divided by the width. So we have depth, which is 20, divided by 20, then we have 1. On the other side here, in single U, depth to width ratio, so we have 20 divided by 10. So in this case, we got 2. So 2 here, meaning it has height depth to width ratio. All right, when it has height depth to width ratio, which is more than or greater than 1.41, then as a result, you got cracking. Yeah, for single U, because of depth is higher than the width, that's one of the factor. High solidification crack can occur. Comparing to single V, the depth to width ratio is less than 1.4, then the theory said unlikely to occur solidification cracking. All right, memorize all this. Okay, they will ask you certainly. All right, okay, for sure. Take photo of this if you want. Okay. So depth to width ratio, yeah, sulfur, and also the thermal stress. That's 3 factor solidification cracking can occur. So please memorize that one, yeah. Especially this one, depth to width ratio. They are like to ask you about this, yeah. All right, and then please, if you can, please memorize a bit about all this, yeah. Control joint fit up, avoidance solidification cracking. Use electrode with high manganese. Highlight this. High manganese better. Why high manganese? If you use electrode with high manganese, so the purpose of manganese, it will form a spherical ball which will tie the grain. The purpose of this manganese will tie up the grain. All right. So that's the good thing about manganese here. So it will avoiding. All right, avoiding solidification cracking. High manganese in the electrode, all right? Avoid high sulfur, reduce sulfur, minimize thermal stress, right? Produce bit with adequate depth to width ratio. So this is related to the statement here, depth to width ratio, all right? So that's the thing you need to memorize a bit in order to avoid solidification cracking, yeah? All right, we move to next slide. Oh, we finished that one. Okay, so it's a very short topic for solidification cracking, but there is few factors avoiding of solidification cracking you need to memorize a bit. Okay. All right. We move to lamellar tearing. All right. In this lamellar tearing, I would like to draw in the whiteboard, and then you may take photo after this. Yeah. Okay. All right, see, we have that's the weld side, and then the first factor here is only occur in T, K, Y corner joint only. Okay? Never in, but well played. If you got two plate like this, never. Okay? But if you got T, you got joint K, corner, all those are possible to have lamellar theory. Okay? Never in but well in plate. Put in your mind, all right? Memorize this. All right, another factor here, the second factor I can write down here is the material ductility. Right, material ductility, when you got low ductility, less than 20% STRA. Okay? And normally occur in thick material. Okay? Normally occur in thick material. That's the second factor. And the third factor I can write down here is the stress directions. So stress direction can be three names they put here: through thickness, and also sometimes they call it short transverse, and also sometimes they call it Z directions. Z directions here, example, we have kind of like X, Y, and that is Z. Right? So what does it mean? It's got three names, but meaning the same thing. Through thickness, short transverse, Z direction meaning the thickness of the material. So the stress acting at the following the thickness of the material. So that means by through thickness, short transverse, Z direction. I don't know which one they're going to ask you or the answer giving you, but normally they come up with the name through thickness, short transverse, Z direction, and then you need to know that that meaning the thickness, the directions of the thickness, the stress acting at the thickness direction. Okay, clear about this? All right. Then another factor, which is I can write down here as a minor factor. Minor factor is the impurities. Meaning acting as initiation point. Like we have kind of like a contamination in the steel making. So that's why impurities here normally, this normally mainly occur in thick material. Yeah. So we have initiation point like void, like impurities, right, in the material. Together with all these factors, then as a result, we got crack occur, which is, they call it lamellar tearing, and also known as step-like cracking or indication. Step-like cracking or step-like indication, because it's formed like this. It's never in slice like that, okay? It's always like jagged. So that's why they call it step-like indication, step-like appearance. Yeah? All right. So this occur during welding, and it occur only in base metal. So that occur in base metal. Base metal cracking. Not in the weldment, not in HSAC. Okay, clear about this? Yeah. We're talking about hydrogen crack. It occurs in the wear metal and HSAC. We're talking about solidification cracking. It only occurs in wear center line. Talking about lamellar tearing, it only occurs in base metal below HSAC. Got it? Yeah. So that things you need to memorize a bit. Okay. So this occurs during welding when during cooling the welds start to shrinkage. During cooling, it starts to shrinkage. So what happens during cooling? It starts to shrinkage. Then this weldment start to pull. They are starting to pull the half of the plate goes up. So the plate now, the half of the plate now pulling up by the weldment, and another half now stay or refrain or restrain. Yeah, so that's why keep pulling, pulling, and the material is low ductile, easy to break. All right, take photo of this now if you want, because I'm going to discuss from your slide after this. Yeah, so all these please memorize. All right. Done? Photo? Got it? Okay. Now I'm going to discuss from your slide. All right, take photo of this. Right, you can see here, this occur at the base metal, yeah? Sorry. Right, this occur at base metal and it produce step light appearance in parametal or base metal. Right, step light appearance. Sometimes they come out with the name step light appearance. So you understand, this referring to lamellar tearing. Okay? And they come out with the terms step light appearance, step light indication. So they are referring to lamellar tearing. Do not confuse with lamination, okay? Do not confuse with the term lamination. Lamination is different story. Got it? All right. Memorize all these. Factors, please memorize. Where I already draw for you based on the factors given here, okay? So occur in susceptible material pore through thickness ductility value less than 20%. If they got more than 20% from STRA, STRA is shock transverse reduction area test. We're going to discuss later about this. Meaning is high ductile. High ductile material. If you got more than 20%, so material got 20% more, so there is no problem with lamellar tearing. So then they also call this is a Z quality. All right? They also call this Z quality. All right? So write down this one. More than 20% STRA, high ductile material, Z quality. So no lamellar lamellar tearing occur. Anything below 20%, yes, you got lamellar tearing. So that's what they try to say here. Yeah. Associated with rolled steel and non-metallic inclusion in steel, this one referred to normally in thick material. Thick material, you got more non-metallic inclusions comparing to thin plate. Yeah. For thick material, you got more impurities. Yeah. Thermal stress, you know, we know thermal stress when the well start to cooling down, then it start to contract, right? Pulling, yeah, contract. All right, we move to next slide. All right, remember this value, less than 20% from STRA, short transverse reduction area. And roll section or non-metallic inclusion, ST contain non-metallic inclusion in varying amount. The hot roll steel, this inclusion are elongated in direction of rolling. This type of internal defect more likely in occur in thick material. All right, highlight this. So you understand, thick material are more susceptible to lamellar tearing. Okay? Thermal stress, this one during cooling, contraction deposit where metal create localized strain. If the localized strain exceed the yield strength of the base material in the true thickness direction, remember true thickness direction is the thickness of the plate, lamellar tearing will result. Okay? So example of this joint, now when they start to contract, you know, another half of the bottom plate now pulling by the weldment, right? Another half plate pulling by the weld, another half stay. So as a result, we got lamellar tearing. So here it says step-like appearance. Memorize a bit. When it says step-like appearance, you understand, this is, they refer to lamellar tearing. Okay? And this is another example when the weldment pulling, all right, pulling both directions, then lamellar tearing can occur. How to avoid lamellar tearing? It said use steel with good true thickness ductility in Z direction. Remember, I mentioned about Z direction, meaning the thickness direction. So good true thickness ductility here, we can say when it's more than 20% STRA. So that means by good true thickness to avoid lamellar tearing. Change joint design, carry out appropriate testing necessary STRA, UT to find lamellar tearing, not to avoid. Okay, UT to find lamellar tearing. It's not to avoid, okay? To find lamellar tearing, to locate lamellar tearing. Yeah? Use buttering. Buttering is like this plate. Let's say there is low ductile plate. So we grind, remove part of the surface, and then we weld with high ductile electrode, like cladding. Then after that, we place the upright T on the top like this. So that is buttering. Yeah? And also try to reduce restraint. Yeah? So this is what they call STRA, short transverse reduction area. But here they call it short tensile reduced area. But sometimes they call it here, like the bottom here, short transverse tensile test. They call it also short transverse reduction area. All right. So what they're doing here, there are friction tests at this point. Friction weld. All right. Then after that, they cut the specimen. And then they pull. All right. They're pulling it, tensile, doing the tensile. This is from manufacturer, not from our fabricator. This is manufacturing. Manufacturing of steel, plate or or pipe. Yeah, not from our side. Fabricator, we don't do this. Yeah. Then they remember in this STRA, they measure diameter before and after in order to get percentage. Remember this. All right. So ductility percentage from the diameter of the specimen. Before and after, they're comparing how many percent. Okay, not from the length, it's from diameter of the specimen in order to get ductility. Yeah. In this theory, CSWIP, there is two ductility percentage we can get. One from diameter, which is under STRA. Another one during tensile, they get from elongation difference. All right, elongation difference. Before test, 50 millimeter. After test, maybe it's increased to 70 millimeters. So what's the difference there in order to get percentage? All right, percentage here, they are referring to ductility. Remember that ductility, there is two ways to get ductility here, percentage. Yeah? Diameter and elongation. All right, we're going to discuss detail under topic mechanical test later. Yeah. And please memorize this. Eh? Please memorize this one. Okay. All right. Remember here, from STRA, short tensile reduced area. They said here anything above 20%, they call it probably freedom from any tearing in any joint type, meaning it's got good ductility. All right. Anything above 20% is good ductility material. And also they call it Z quality. Remember? When they say you got Z quality from Milset, this mentions Z quality, meaning the test already done and it's more than 20%. Yeah? It's a good ductile material. Then no danger of lamellar tearing. Clear about this? Memorize this, 20%. Memorize, eh? So how to avoid lamellar tearing? Maybe we buttering. Buttering means we weld with hard ductile electrode at this point. All right, hard ductile electrode. And change your design. If we bevel this side, maybe crack will be this side. So bevel this side, there is no crack. Okay, no bevel this side. Or maybe butt weld, all this butt weld. Forging teeth, then we got butt weld. Yeah? So there is no problem lamellar tearing here. Okay. Questions. You are working as senior welding inspector during fabrication and welding of topside module. The module fabricated from carbon manganese and the carbon equivalent is 0.46. Yeah? It's quite high percentage of carbon equivalent. Certain section fabricated from universal beam with thickness ranging from 12.5 to 50 millimeter. And again, the plate also the same thickness. All right, look at question 1. One of your inspector, all right, this is no spec. Question 2. I think this one also no spec required. 3. There's also no spec. 4. No spec. 5. Again, it's no spec. 6. No spec. 7. So there is no spec. 8, no spec. 9, no spec. 10, no spec. All right, looks like all the questions, 10 questions, not referring to any spec. And again, do it as your homework. All right, we discuss tomorrow, 6:30, same time. Yeah. All right, look at question number 1. One of your inspectors suggests you that lamellar tearing have occurred in single bevel butt joint. So that statement already wrong here. Remember, lamellar tearing only occur in joint like T, K, Y, corner only. Never in butt weld, never in single plate butt weld, never. Okay? So that's where the answer goes to D. All options are incorrect because the answer is here, yes, can occur in single V, so that's wrong. No, this type of defect will occur carbon manganese carbon equivalent, so that's also wrong because of talking about carbon equivalent. This only apply for hydrogen cracking. See, yes, this defect possible, single bevel, that's also wrong statement here. Yeah, all right. Number 2, you notice from WPS on certain joint, preheat 150 degrees C is required. On other joint, preheat is only 75. Why do you think some joint require more preheat than other? All right, please memorize this one. The factor for preheat, where you don't have it in your slide, take photo of this. Yeah. Memorize. All right, so this is factor for preheat. We got 4 factors: heat input, carbon equivalent, hydrogen, thickness. So heat input increase here. So we got it from formula heat input. So heat input equal to arc energy times K factor, where arc energy equal to volt times m's divided by travel speed. And then we times with K factor here. So how to get heat input increase? Heat input can be increased by having amps increase, voltage increase, or maybe we reduce the travel speed. So we got high heat input. Yeah. So when the high heat input, increase heat input, then preheat can be reduced, or vice versa. If you reduce heat input, preheat before welding must be higher. So that is the factor for preheat. Another factor, which is equal, all right, equal to, if you increase carbon, percentage carbon increase, so do for the preheat also increase. If you lower, preheat lower. Hydrogen, example, you're using cellulose electrode, rutile electrode, which is high hydrogen. When you're using process with high hydrogen, so the preheat must be higher. Yeah. And the same thing goes to thickness. If you're using high thickness, the thickness of the material higher, then preheat must be higher. The only difference here is the welding heat input, inverse proportion. This side increase, this side lower. This side lower, this side increase. That only apply for heat input when we relate to preheat. Okay, the other factor, the other 3 factor is equal. This side increase, this side increase. Okay, please memorize this. All this you must memorize. Take photo of this now. Okay. All right. Now back to your question and answer. All right. So from here, you say They're talking about preheat. So remember, there is 4 factor under preheat, which is heat input, the factor of carbon equivalent, the factor of hydrogen, and the factor of thickness, material thickness. That's 4 factor. All right. Why do you think some gens require more preheat than others? That's the question I ask. All right. Here, the answer is wrong because of solidification cracking is not related to preheat factor. This preheat factor related to hydrogen cracking. That's for sure. You see the factor. Yesterday, I have asked you to memorize the factor for hydrogen. So one of the factor is carbon equivalent, all right, which is carbon percentage, which will affect the hardness, and also microstructure, right? All right, the answer C, why is wrong? You said this will be due to the fact some welder require more preheat. It's not a welder. This is WPS. So the welder must follow WPS. It's not requirement by welder. So all option incorrect is due to lamellar tearing. That's also wrong statement. So the best answer goes to B. This will be due to different thickness of metal being used and increased chances of hydrogen crack. All right. And if you look at question number 3, it's related to question number 2. You see here, question 3, that confirms the purpose of preheat. He said preheat are too low to prevent hydrogen crack. So that related to question number 2. Yeah, the purpose of preheat here to avoid hydrogen crack. All right, which of the following combination are correct determining correct preheat temperature? So again, remember preheat, that is 4 factor, heat input, carbon equivalent, all right, hydrogen, and material thickness. Yeah. So look at A, why this is wrong. You say material thickness, correct. Joint design is not a factor. Amount of hydrogen, yes. Welding process basically is related to amount of hydrogen. Yeah, should be okay. B, thickness, correct. Amount of stress is not a factor for preheat. Hydrogen content, yes. Carbon equivalent, yes. But since we got one answer wrong under B, so that's why B is wrong, A is wrong. How about D, amount of stress? That's wrong. Welding process, if it's related to hydrogen content, then okay. Carbon equivalent value, yes. So the best answer is C, right? Material type, meaning it's referred to carbon equivalent, thickness, yes. Hydrogen, yes. And heat input, yes. All right, so that's where the answer goes to C for question number 3. Yeah, all right? Agree with that?
Agree.
All right, we move to question 4. One of your inspector asks you what are the main factors affecting hydrogen crack. Right. The answer goes to A, yes, because temperature when it's less than 300 degrees C, amount of stress when it's more than 0.5, yield strength, molecular group of hydrogen, that's correct. Material composition, yes, because it's related to carbon equivalent. Why B is wrong? Because it's not related to thickness. Factor of hydrogen never relate to thickness unless we refer to preheat. Factor, yes. Atomic hydrogen is wrong because they ask for molecular. Molecule group, yes. Atom is single, is not the factor. right? Talking about process of hydrogen crack. Material composition, yes. Amount of stress, yes. Sulfur, no. C is wrong. Sulfur is the factor for solidification, cracking. Hydrogen content, yes. Amount of stress, yes. Material composition, yes. Right? So that's where the answer goes to A only. That's the best answer. Got it? Okay, number 4. Number 5, during visual inspection, one of the inspector detect longitudinal crack along the well, center line approximately 100 mm, which are the four reasons for the occurrence of the crack. They only give us two elements here, which is sulfur and manganese. Remember yesterday I talked about manganese. Manganese, if you have electrode with high manganese, manganese will form a spherical ball in order to tie the grain structure. So that's the purpose of manganese. If we have high manganese, that's very good to avoid solidification cracking. Yeah? If you got high manganese, avoiding solidification crack. Got it? Right. So B is the best answer because we got very high sulfur. Sulfur, remember, is the main, one of the main factors solidification cracking to occur. You got high sulfur, all right? That's the main, one of the main factors solidification cracking. And manganese content too low, yes. Because when you got low manganese, manganese didn't give any effect in order to tie, bonding the grain. There is no effects at all. If you got high manganese, yeah, that's okay. Manganese will give bonding between grain. All right? 6, one of your welding inspector informed you that during welding, one of the welder using long arc length. All right, long arc length here, we understand, yesterday I think we have talked about this, when we got long arc length, so the electrode, and then we got the base metal here, or parameter. So we got very long arc length. So what happened?
Thick sikit kopi.
If you got long arc length, meaning not enough coverage, not enough shielding. So when not enough shielding, hydrogen can enter. All right, so it will increase the hydrogen level. All right, so this talking about hydrogen cracking. Yeah, so that's where the answer goes to A. Why B is wrong? Because carbide precipitation, this one we're talking about well decay factor in stainless. Increased risk of solidification crack is wrong. Because hydrogen is not factor in solidification cracking. Sulfur, joint design, thermal stress, that is what in solidification cracking. And also D is wrong because of hydrogen is not a factor in lamellar tearing. It's only TK1, joint, low ductile material, that's a factor for lamellar tearing. Okay? All right, 7, when inspecting material certificate, you notice some material class as Z steel or Z quality material. We understand when they say Z steel, meaning this type of material got good ductility or good true thickness ductility, where the percentage from STRA, short tensile reduction area, which is more than 20%. It's a good ductile, more than 20%, that is that quality. So meaning it's related to lamellar tearing. All right, related to lamellar tearing. But we have Z quality, mean there is no problem with lamellar tearing. So that's why here A is wrong, because they're talking about solidification cracking is not a factor. Hydrogen cracking is not a factor, but C is correct because they talk about lamellar tearing. Okay? All right, 8. Which of the following could be used to prevent hydrogen crack? All right, the answer A is wrong here. Why? We know this is basic. Yeah, that's okay. That's basic electro. We know that it's less than 5 milliliter, but now it said use basic in standard package, meaning this one is no bake. Standard package here means no bake. It's no baking. When it's no baking, the hydrogen level is still higher. Okay, it's high hydrogen, so we cannot prevent hydrogen crack. So that's why A is wrong answer. B, 8010, this is cellulose, where we know that this hydrogen level in between 80 to 90 milliliter, which is high hydrogen, and must not bake. If you bake, you damage the electrode. All right, that's wrong statement here. This one, 6012, this is rutile. Use in dry condition will give lower UTS value, which give increased elongation. That's also wrong, because rutile here got in between 20 to 30 milliliter per 100 grams. So that is wrong also. So D is the best answer. All options incorrect. Because read carefully, say prevent hydrogen crack. A, B, C cannot prevent the hydrogen crack. Okay? All right, 9. One of your inspectors suggests increasing restraint to reduce distortion. Yeah? In single V butt joint. We understand restraint means the material not free to move. Not free to move. That's what we understand about restraint. So during welding, the material is fixed. It's not moving. When it's fixed, no distortion. That's correct. But very high stress. Because, you know, not moving. Someone tie you, put it in the room for 10 hours. So what do you feel? You feel very high stress because you cannot move. That's the same thing here. Okay? All right. Single V butt joint. So that's why we have lamellar tearing answer here is wrong. Remember, lamellar tearing never occur in single V butt joint. All right. And this one, weld decay is not from the residual stress. Weld decay here because of carbon mixed with chromium. So that will be in stainless steel. All right, so the only choice we have is hydrogen crack, yes, and also because of restraint during welding, it will create thermal stress. So in certification, it will create thermal stress. Okay. Here is thermal stress. And here, residual. For hydrogen crack, residual stress. Yeah, but that's because of restraint too. Residual stress, thermal stress because of restraint. Yeah. All right. Number 10, last questions. During inspection of material prior to fabrication, one of the NDT inspector report back to you that he has detected lamellar defect running in the center of the parent plate prior to fabrication, meaning that is before welding. So before welding, you didn't get any type of crack. You didn't get hydrogen, you don't have solidification, you don't have lamellar tearing. Yeah, because that's prior, before welding. And also this one talking about the plate. All right, so this statement about lamellar tearing is wrong. Okay, because of its parent plate and before welding. So the best answer goes to A. This is very straightforward questions. I don't think that all of you difficult to answer. Yeah. All right.